We're going to talk about relations and functions today, but first of all, of course, let's start that lesson opener so you pause and then come back and check your answers.
Okay, let's see how you did. So the first one says simplify the expression. So after you go ahead and distribute, now be careful when you distribute because you have that little negative sign there. Put a little -1 there if you need it. You combine like terms and you should end up with 3h plus 3g. No big deal.
Notice that you don't have anything equals. We didn't get g equals 2. Why? Because it's an expression. You can simplify expressions. You can solve equations, which takes us
to the second one where it says solve the equation. So we're going to end up with a solution here like x equals or a equals. So for this one, after I distribute, I'd go ahead, get my variables to one side, isolate that variable, and I end up with p equals 2.
Essential vocabulary. So remember to get this down. Very important. We communicate effectively in math. Relation is a set of pairs of inputs and output values. So everything that we're dealing with today will be a relation. To be more specific within that relation, if we're talking about the inputs, that's the domain. And so if we're talking about an XY ordered pair, the X coordinates are the inputs. And it's also known as the independent variable. Range then, of course, is the output of any relation. In an ordered pair, the y coordinates, and we call it the dependent variable. We call it the dependent variable because it depends on the value of x. Whatever the input was, then it shoots out the output. So let's get to it.
Did you write those down though? If you didn't write those down, pause and make sure you get these written. Moving on, we have different ways we can represent a relation. Here are 4 good examples of how you can represent a relation. A set of ordered pairs, a mapping diagram, a table of values, or a graph.
Within those, we're going to look at 2 in particular and talk about the domain and range. So that first one, the set of ordered pairs, we have the domain, which is going to be the x coordinates, and we'll just go ahead and list those in order from least to greatest. Very important. We also use that curly Q bracket. That tells us it's a set of numbers. So we start with -2, then 1, and then I see 5 appears twice, but guess what? When I talk about the domain, I only have to write it once. With the range, we go ahead and look at the y coordinates, same thing, least to greatest, and that means we'll have -7, 11, 21. I did not write the 11 twice. The next one we look at is just that mapping diagram, and we didn't take time to write all this out, but just to emphasize, remember that the inputs are the domain, so that -1, 0, 1, 2, 3, and then the arrows are pointing to the outputs, so that column is going to be the range. And then similarly, if you look at the table of values, the inputs, you would list that as your domain, the outputs, that's your range. Then we get to the graph, and the graph has a set of points. So sometimes students like to write these out separately on the side, but we can also just stop and think about it. The domain is the x coordinate. So if I walk along that x-axis and I look up and down, I can see that the first point I come to occurs when x is -3. So I can write -3. Then I go to the next one, -1, and so on, all the way along. So I end up with -3, -1, 1, 2, 3. When I go to do the range, I look at the y, and so then I'm going to go walk up the y-axis, and I'll start, and the first point that I get to is over there at -3. So -3, keep walking, I see 1 at -2, keep walking, 1 and 2. The range is -3, -2, 1, 2.
This brings us to what a function is. Now, a function is just a relation in which every input has exactly one unique output. So like every x maps to exactly one y.
Right, they can all map to the same y, but you're never going to see like a 5 going to a -7 and a 5 going to an 11. So if you look at that first ordered pairs, right, that's not a function because 5 is going to -7 and to 11. And then we can talk about a very special type of function, which is a one-to-one function. So once again, it's a function, so we know that each input maps to exactly one unique output. But if it's one-to-one, then each output maps to exactly one unique input. So you don't see repeats either way. So if we look up here at the representations of relations, we're going to go through and kind of categorize everything. I gave away that first one, the ordered pairs, because we already know that's not a function because 5 goes to -7 and 5 also goes to 11. So boo. Now, it's okay that -2 goes to 11 and 5 goes to 11. It's still a function. So a function just doesn't have where the x goes to 2 different y's. But all of them could go to the same y.
Moving on to the next one, this one is a function. So in our mapping diagram, we can see that every input has exactly one unique output. But is it a one-to-one function? Let's look at those outputs. No, that output of 1 has 2 different inputs.
So that doesn't work. When we look at the next one, now I think we're going to see a one-to-one function because -2.1 goes to only one output, negative 4.2. I'm not seeing any of the x's repeated. I'm not seeing any of the y's repeated. Now looking at the graph, I'm trying to check if it's a function or not. If I look along at that domain, I see we have this unique domain, negative 3, negative 1, etc. And each x value only goes to one y value, which leads us to that vertical line test. So if we want to jump down there, the vertical line test says, if you're looking at any sort of a graph and you draw a vertical line, if it goes through more than one point, if that vertical line goes through more than one point, then it's not a function. So if we look at our graph, it's just a collection of points, but there are no 2 points that occur on the same vertical line. So our graph is a function. But let's look a little bit more at vertical line test and see if we understand it.
Okay, so make sure you wrote down that definition for the vertical line test, and then as I move down to these bottom 3 graphs, the first question is, which are not functions? So if I look down here, I'm just gonna run the vertical line test across all of them. The first one totally passes the vertical line test. Nowhere I draw a vertical line am I gonna pass more than 1 point. Same with the second one. But then I move to the third one, I could draw a vertical line on this one, and I'm crossing twice because it's a circle. It's gonna intersect my vertical line twice. So C is not a function, so I can say that right away. The other 2 are functions, I just need to figure out what kind of functions they are. So when it says which are functions, I'm gonna say A and B, and then 1 to 1. Okay, so 1 to 1 says every input has one unique output, and every output also has one unique input.
So if we have the vertical line test to test if every input has one unique output, could we use a horizontal line test to see if every output has one unique input? Yes, we can. Be careful with that, and I hope we're not giving you too much information. Vertical line test tests for function, and then vertical line test and horizontal line test would test for a one-to-one function. But for the most part, we're just looking at functions. So keep in mind that's the vertical line test.
So since A and B both pass the vertical line test, I can now run the horizontal line test on them. If I run the horizontal line test on A, totally doesn't pass. I could cross like up to like 3 times. But if I run it on B, since it's a straight line, I'm only crossing the horizontal line once at any given point. So yes, B is a 1 to 1.
And pretty much every line that does not happen to be a vertical or horizontal line is a one-to-one function.
So let's check our understanding here. If I just want to check to see if my graph is a function, what do I do?
We use the vertical line test, and if that vertical line anywhere on the graph goes through more than 1 point, it is not a function.
So then why would I ever need the horizontal line test?
Only if somebody's asking you specifically if it's a one-to-one function. And then we also use it for something later on in class. If a relation is a function, it's often very useful to use function notation. Now, function notation, we use it for a couple of reasons. 1, it's an efficient way to talk about multiple functions at once. And then 2, if you give me an input, it's a quick way to ask the question for the output. So you'll see that in a moment. I'm going to walk you through the idea behind function notation. So take a look at the given function, y equals 2x minus 5. What is the independent variable or the input?
X.
And then if we talk about the output or the dependent variable, we have y. So y depends on x, and we would say y is a function of x. Then we could write it as y equals f parentheses x, function of x. So that's how we write the function notation. Y is the same as f of x.
Okay, let's go ahead and rewrite that function above then. Using substitution property, I can now say f of x equals 2x minus 5.
And the way we read that is f of x. I know we've said that a couple of times, but it might help you to write that in. F of x equals, and then 2x minus 5.
Perfect. So now we know f of x is our output, x is our input.
Now that we have f of x equals 2x minus 5, I said that it was an effective way to ask for an output given an input. So look at our example, f and then parentheses 2. What changed there? The x became a 2. Well, this is why it's a nice, efficient way of doing it. The input is 2, and I go ahead and rewrite that f of x equals 2x minus 5 above it, and I notice that the x has been replaced by 2, so I go on the other side and I replace the x by 2. So f of 2 equals 2 times 2 minus 5. 4 minus 5, negative 1. So f of 2 equals negative 1. Do not be tempted to divide out 2. Remember, this is not function notation. It's not f times 2.
For the next one, it looks like we have f of negative 3. So my input this time is x equals negative 3. Same function, so I'm just going to replace my x with negative 3, and I get f of negative 3 equals negative 11.
So now, of course, we want to make sure you can do it. We're going to change the function. There is no special magic to f, although it's pretty cool, function of x. But the next function, we're going to go ahead and call it m of x, and really it can be any variable. My input is still the x, so whatever's in those parentheses is the input, and then the m of or f of, it could be anything, right? That's the output. So m of x equals negative 4x plus 1, and we want you to pause the video, try the problems, come back and check your answers.
Okay, let's see how you did. A should be m of negative 2 equals 9, B should be m of 0 equals 1, and then C should be m of 5 equals negative 19. You can pause and check your work if you need to.
All right, let's get to the next one. Now I said another use for function notation is it's an efficient way to talk about multiple functions at once. So look at number 4. I've given you 3 different functions, but we know which is which because if I say g of x, you know that you should be looking at that middle function. If I say h of x, you should be looking at the third function, and so on. So then when you look at the question, A says g of 5, g, where do I plug that 5 in? Well, I plug the 5 in to the g of x equation. So g of 5 equals 4 minus 2 times 5, figure that problem out, and so on. Pause the video, try the rest. Alrighty, so g of 5 is negative 6, h of 4 is 5, and our last one, f of negative 1 equals negative 4. I hope you did great. If you had a problem, pause it, look at all of the work, check your answer. Last but not least,
of course, we want to get some actual application here, so let's look at 5. So 5, we're going to go ahead and write a function notation, and kind of evaluate this situation. So let's see what it is. We got write a function rule, an equation, to model the cost of renting a truck for 1 day. So we're given the daily rental fee, so $19.95, pretty good deal if I just want to rent a truck for 1 day and sit in it, $19.95. And then the rate per mile, so that's in addition to my daily fee,
is 50 cents per mile.
so the total cost of renting the truck depends on how many miles I drive. So it looks like cost depends on miles. So we could make a function and we'll call it like C of M. Cost depends on miles, or cost is a function of miles. So let's make sure we define a variable. M is going to be our miles driven and C is going to be our total cost. So $19.95 plus every single mile I drive, I'm getting charged 50 cents, so 0.5 M. Okay, so then part B, we have our function rule written. So part B wants us to determine the cost if we traveled in that truck 73 miles.
so now make sure you use the proper notation. C of m, we're going to replace m with 73. So we're going to say C of 73 equals, and then plug that 73 in for m. So 1995 plus 0.5 times 73.
And we get 56.45, so $56.45.
Hey, do you think this is an okay place to use a calculator?
Yeah, there's decimals.
I mean, I guess you could use a calculator here. Remember, overall though, we want to try and not use calculators for every little thing. Like if you punch 2 times 3 into your calculator, no. One of the things we want to focus on this year is making sure that when we are answering a real life question, that we write out the final answer in context of the problem. So, Miss Ryan,
if you've driven 73 miles, the cost of renting the truck for 1 day is $56.45.